this back panel from an old radio, Harry's TV repair sticker. It has a date on it, 9/20/66. So Harry's TV serviced this radio back in 1966. I doubt that phone number is extant. Cold Spring Lane at Reisterstown Road. I know where that is. Interesting. Well, the radio from which this came locally. It was a Zenith. It's been, let me say, repurposed. It was the radio from which this came was well beyond economical repair. It was kind of a piece of junk. It's sitting right here. There's some useful components out of it. Nice clock. A couple of coils. And this. The back panel. The reason we're looking at this is it has the antenna on it. A loop antenna. And it's just a number of turns of Litz wire. Single coil. And the terminations for it over here. Let me go over a little bit about these things. They're useful in a number of ways once liberated from the radio. But first maybe go over some of the characteristics of these things. Of course it has some inductance. It's the whole point of it. It also has distributed capacitance associated with it because of the proximity of the windings and other things. So, as it is by itself, just a coil of wire mounted to a piece of wood, fake wood, native wood, it will self-resonate fairly well, actually. Now, of course, in the radio, there's a capacitor connected across this, which is the tuning capacitor, the tuner capacitor. This guy. That brings this into resonance for the frequency of interest. That is the station you're tuned to, of course. But by itself, just without any capacitor tied across it, except for the probe capacitance here of my oscilloscope, which, according to this, markings on the probe is 13 picofarads. Well, that's pretty small. So I'm going to connect the scope directly across this coil, this loop, and there's nothing there. What would I expect there to be? However, I'm just going to lay this here. It's a wooden table, so there's no metal to affect the tuning of this or anything else. Get this tucked out of the way here. So, scopes across this loop. It's got a signal generator here. It's also tied to this counter, so I can read out the frequency. It's tuned to 436 kilohertz. This I'm not going to connect electrically to anything. I'm just going to lay it here on top. This is a typical lead out from a frequency counter with coaxial cable with a couple of clips. Now I'm just clipping the ground to itself just to keep it from being unruly. And I'm just going to lay this. This has got about 20 volts peak to peak of RF on it. The way I have this dialed in, actually it's all the way up. So it's about 20 volts peak to peak, but it's enough to couple into this loop, just capacitively, electrostatically. Just lay this down on top of there like that. Now, there's no response from the coil into the scope because it's not in resonance to this frequency. I'm going to dial that up, and you will see it begin to show on the scope here. Well, there's a little peak there. just about a megahertz. There's, oh, look at that big old peak. Loosen this up a little bit. So you can see quite a bit of signal coming out of this. Just me getting near it changes its capacitance, and coupling and so forth, and changes its resonant frequency. But right now, this, without any capacitor across it, is resonating just about 2 megahertz. 2 megahertz. Which means if we go down to half of that, it'll resonate there a little bit too. Just about 1 megahertz. Same rules apply if I change capacitance. So, you know, there are drawing a blank. Sidebands that these will resonate at somewhat, but the peak is right there, a little over 2 megahertz, very much a little over 2 megahertz. But so for AM broadcast band, that's a little high. Typically, it go from, you know, call it 550 to 1600 kilohertz, or 0.5 something to 1.6 megahertz. So, you know, without any capacitor tied across this to tune it, it self-resonates at 2 megahertz. Handy to know if you're going to use these for other purposes. And notice every time I get my hand near this, it changes the response. So let me put my hand on it a little bit and retune. Well, it's tuning a little bit at a somewhat lower frequency, and the Q isn't as high. You can't get the same amplitude out of it. Probably because I'm bleeding off some of the signal. So, without my hand near it, and without any added capacitance, and that's where it resonates. 2 megahertz. Just a little bit above 2 megahertz. So, bring on the tuning capacitor. This is actually, it came out of the radio from which this back panel and antenna did. It's got 2 sections. One of them, the larger of the two, is actually what tuned this antenna coil. This other smaller one tuned the oscillator in the radio, superhead. The oscillator frequency is 450 kilohertz or thereabouts higher than the signal coming in, so this needed to be a smaller capacitance to dial in. Don't want to get too much into those details, but what we're interested in is this section, this capacitor. A pretty simple deal. There's a couple of clip leads on here. One to the frame, which is connected to the movable plates. The other to these stationary plates. There's also a trimmer here. We don't need to worry about that right now. So I'm going to connect the frame to the where the scope is connected, the ground, low side, and I'm going to connect this stator for this capacitor to the high side. And you'll notice as soon as I attach this, we lose all signal. It's because it's now tuned to a different frequency. It's not really picking up so much. There's a little bit, but not as much. So let's get this down to a reasonable, let's call it, that's 1600 kilohertz. Let's get it very close. Yeah, close enough. and see where we dial. So it's actually peaking almost all the way open. If I go truly all the way open, that means the minimum capacitance. It actually loses a little bit of amplitude. Let's crank this up a little bit, make it easier to see. So that's fully open, and that's just a little bit less than open. And so it's resonating right now with this capacitor all the way up, nearly all the way open at 1600 kilohertz, or 1.6 megahertz. Now, close the gap, or close the place a little bit. Of course, it pulls it out of resonance at that frequency. So, where is it now? The plates are fully meshed, full capacitance. Keep in mind, you add capacitance or add inductance. It will decrease the resonant frequency, which this has done. So, just roll this back until we get a peak. Let's make that a little clearer to see. Where is it peaking now? Oh, it's really sharp. 505 kilohertz, or 0.5 megahertz. So this is easily made to resonate and changeable via this capacitor, which is how it works in the radio, from 1.6 megahertz to 0.5 megahertz, the AM broadcast bands. Of course, if I tune away, you'll find other places, usually multiples of the frequency, especially even ones. So let's say it's resonating at, let's call it 500 kilohertz, 0.5 megahertz. And where's this other point? Seems to be a little peak there. I'll bet you that's twice 500. Well, looky there. Of course it is. That's how it works. So that's a useful thing to know. These things work pretty much the same way these do. Now, my coupling here is very, very loose. I mean, there's no connection to it at all, other than the earth safety ground. The actual signal is just this very short length of wire, and all you got to do is get it near. When this thing's in resonance, the frequency coming out of here, it's pretty hot. So that's how that works. There's another aspect of these that seems to escape some folks' notice, radio guys notice. Just to clarify things, I'm going to get rid of this capacitor here, this tuner. I think that point's being made. Interesting effect there. Yeah, it's, without the cap, it's somewhat freaky. Jeez. So, should be, no, a little bit of looseness here with this probe. Anyway, so that 2 megahertz without the tuning cap. But watch what happens. Now, normally with these types of circuits, these things, if you're familiar, you know that they have powdered iron or ferrite slugs in there, call them screws, that you move in and out of the coils contained within something like this. These coils here, they're not much different than this, just they're not meant to receive or pick up from remote locations any RF. They're meant to be resonant and transfer energy from one coil to the other. only the energy you want, which is of a certain frequency. And that's why they're tuned, of course. You know, they've got the ferrite or magnetic slugs. It doesn't mean they're magnets. It just means that they'll convey magnetic flux. And putting those slugs further into the coil increases its inductance, of course, which would tend to lower the resonant frequency of that coil. At least typically, this is an IF can from a radio, 455 kilohertz or 0.555 megahertz. And there's a separate slug. There's one down the bottom, one up the top. And those, each slug tunes each coil. But then there's this can, this aluminum can. Most folks that do this don't really fully get the function of this can. It is an electrostatic shield. It needs to be that, meaning it does. They don't want this. You don't want. Nobody wants this receiving signals from adjacent components in the radio or from elsewhere. It's only. It's got to be shielded, electrostatically shielded, somewhat electromagnetically, but for the purposes of AM radio, FM radio, we're used to this sort of shielding is adequate. But it does play another role. Two things that seem to be overlooked and unexpected from some guys. It acts as another means of coupling the two coils together. You must think of this can as another coil. It's a very, very short one. Call it one turn. As such, it's a pretty good magnetic shield electromagnetic shield at the operating frequency of it. Certainly a good electrostatic shield because it's aluminum, and aluminum being a very good electrical conductor is not going to let capacitive coupling through this, as long as the can is properly connected to ground as usual. But the can, because those are, if you think of the can as shorted turns, it has the opposite effect that these slugs do. The magnetic ferrous slugs, as you draw them toward the coil, increase the inductance and therefore lower the resonant frequency of the circuit, the coil with its capacitor. Aluminum is not magnetic. You draw a magnet up to it, it will not stick, right? But is a very good electrical conductor, so it actually shorted turns. That has the exact opposite effect. If you draw this near the coils, it increases their resonant frequency. So it must be assumed that this therefore decreases the inductance of the coil. This is not, apparently it's not well known. It's easy to understand, actually, when you get right down to it, but a lot of guys, they seem to, they don't seem to be aware of that. So I can demonstrate this here with this large antenna coil here. Let's set this aside. So, see, we're peaking at pretty stable. Let's call it 2 megahertz. And I'm going to take this can. It's an aluminum can. Just happen to have this handy. You could use a soda can or anything, soda in it or not, it doesn't matter. But this represents a larger sort of can like this. It does not matter, my probe here is wagging. It does not matter whether the can is within or without of the coil, or inside or outside of it. In this case, the shorted turns are outside of the coils, but the effect is the same. So I'm going to take this aluminum shorted turn, and I'm just going to lay it down on here. Look how sensitive that is. And it's not just because I'm holding on to it in the capacitive effects, because I'll set this down and let go. Detuned it quite a bit. Not completely, but it did detune it. So which way did it go? You know, were I to add a ferrous material to this, a magnetic material to that, it would change in the direction of increasing the inductance of the coil, and so lowering its resonant frequency. Putting this can in, this aluminum can in here, could be copper, anything that's non-magnetic that's good, a good conductor will have the same effect by varying degrees. So we'll see where it peaks now. Well, peaks at 2.13 megahertz, so a little bit higher. The effect could be enhanced if I added more aluminum with my hands. You can see how sharp the Q on this is. I mean, just slightest change changes its resonant frequency. Pull this away, back down to a smaller signal, decrease the frequency of the input energy, right back to 2 megahertz. So, good to know. If you're using one of these for something, and a couple of points about that in a minute, you can tune it downward by putting a capacitor across it. You can also tune it higher by putting some aluminum near it like that. A couple of these. This has cheese dip in it, I think. But anything you got that's more or less this, made of aluminum or copper will work. You can actually increase the resonant frequency of these loops. Also true with these cans. It's very it's crucial. If you're going to do testing on these, whether they're in the radio or out of circuit and just connect it up to your gear, do it with the cover on. It makes all the difference. In fact, in the end, you're going to have to peak everything for these things with this installed in the radio. The cover, this aluminum shield, properly connected to wherever the manufacturer originally had it, wired just the same. Phase matters with these things, so you do have to pay attention to that. But don't forget what the role of this can is more than just shielding. It is actually having an effect on the Q, that is the sharpness of the coupling, the amount of coupling, the actual resonant frequency of the coils. It's all designed in. The can is definitely taken into consideration when this was designed. All of them are that way. Don't forget that. And that aluminum shorted turn has a fairly drastic effect on the tuning of these coils. Whether it's a big old antenna like this or something like that, or something that's big as your pinky finger, it does matter. So I think that about covers that. Now, what else these are handy for? In fact, can be quite handy for. If you work on radios that use this sort of antenna, and you're doing an alignment, that's very handy to connect to your signal generator rather than the scope. And just connect the signal generator right across it. And you don't really even need to tune the thing, but it makes a pretty good RF radiator. It's close enough to resonance from 400 kilohertz all the way up to a couple of megahertz. It'll work. But rather than tie your signal generator's output directly into the radio you're working on or servicing or building, it's better to have it loosely coupled using something like this. Just tie your signal generator across it, put it a foot or so away from what the radio you're working on. If it's working at all, you'll be able to get signal through. It's much better way. Connecting in directly is rife with hazards and can cause some head scratching, because the connection it changes capacitances in circuit, and it can cause some grief, at least some uncertainty. Another use for these, if you are interested in long distance, very directional radio reception on the AM broadcast band, so you've got a crystal set. A couple of these placed on either side of your receiving antenna. In other words, say you've got two of these loose panels like this, and each one has its own capacitor, its own tuning capacitor. So you can tweak what frequencies this resonates at, and you've got one on either side of your antenna that's actually connected into the receiver. You can make a very directional antenna, one where it enhances the signal from one side and damps the signal from the back. And so through this and a bunch of dialing and some tedium, you really can get a very directional setup. I've done it, I've seen it done, and it can work quite well. It's tedious, a lot of tuning and distance from the distance between these, let's call them resonators, and your receiving antenna, assuming it's built similarly to this, doesn't have to be exact. It can work quite well. So these, if you get hold an old radio, even if the radio's scrap, hang on to the antenna in it. They come in quite handy if you're planning on working on these things and for other stuff. I had in mind a while ago to build a what do they call them? Shadow box radio, where all of the a shadow box is. You've seen them. It's a thick, sort of looks like a picture frame, but it's got depth. Usually a glass pane in front. I was considering making a tube radio into one of those with like sort of shelves and some tubes. You can see everything, and using, if not this very antenna, something similar to it for the receiver part. It's just a simple American 5 AM radio, but spread out in a nice shadow box. You can see it. See tubes light up, and maybe have this on a hinge up top so you could swing it to get. These are directional just by themselves. You may have noticed you pick up a table radio and turn it, they'll fade and boost depending on its orientation to the transmitter. So just some thoughts about that. But anyway, I hope just shed some light. Maybe hope people gain a little bit of insight about some of this stuff. Oh well. See you.